Oh, thank you. I'm going to consider a follow-up question where mu here is not 0, but equal, let's say, mu1. Okay, so this is a bonus question. Okay. Okay, swimming pool. Yeah, again, those of you who thought about this problem, you figured out the main feature here, that given this ratio, 4:1, if the student is inside the inner circle, so if the student is inside this inner circle, think of this as rotational motion. Teacher running around is like obviously rotational motion, but student can also swim around. So if the student is inside this circle, say this is little r, and little r equals 1/4 of r. Okay, then student actually has a greater angular velocity than teacher inside the circle. And on the border, it has exactly the same angular velocity as the teacher. Okay, make sense? What does it mean for the problem? That means no matter where the teacher is, the student can always outswim him and place himself on the opposite side of the diameter. That is the maximum possible distance between the teacher and the student if you stay on the circle. Make sense? If the student goes outside of the circle, this is no longer true because the angular speed of the teacher becomes faster than students. Okay, so you may not claim that student can always be on the opposite side. But for the borderline, yes. So this red dot represents, without loss of generality, can assume that the student starts here. Starts at the smallest circle. Opposite side to teacher. Actually, I just realized, is everybody feeling fine with circular motion? Everybody understands the concept of angular velocity? Yeah, let me know if anything is unclear. Especially with the other students who are not here, check with them if they understand that. Okay. That what does this mean then? From here, like, what is the closest point on the water of the swimming pool to the red point?
You draw a line connecting the center to that point, and then wherever that line hits the.
So yeah, if the student swims along a diameter through this point, yes. So this orange line is the fastest path. Okay. Or the shortest path to escape.
The length of that path would be n-1 times r over r, where n is the multiplier of the speed.
Oh yeah, I saw your solution, Abhijit. Yeah, so let's stick with the 4 for now, but yeah, that's all good. So this is basically big R minus little r, which is r minus r over n. So this is the path length for the student. Then the idea is that this is the distance for the student. And distance for the teacher to here is along the circle, half of the circumference. That is pi r. Okay. So since the teacher is running 4 times as fast or n times as fast, you need student's time, or if you just talk about distance, you need this distance to be 4 times or less than 1/4 of this. Okay, so the escape is successful if ds is less than 1/4 of dt. I don't actually want to use n because Abhijit, there is a catch here. If n becomes larger, this distance, the orange distance, is no longer the shortest. For example, if you go sideways, it becomes shorter.
Oh, okay.
Yeah.
But how do we know that that straight line is the optimal path?
We don't, but this is the nice part about part 1. You don't have to. So if you present a strategy that works, you're good, right? So the question is there a strategy to escape? If you present that and it works, then you're good.
But what about
Question 2, you have to be super thoughtful, right? You have to actually see which strategy is better and what is the best, which gives you the maximum possible speed ratio. So we'll revisit this question when we get to question 2. And that probably won't happen today, okay? Maybe at the end if we have time. But anyhow, to finish this off, I'm gonna put n equal 4 now. So we got 3/4 of r less than pi r.
Over 4.
Over 4. And indeed this works, right? Because 3 is less than pi. And you can also check if you put the n for this particular strategy. That's what Abhijit did, and we'll use that estimate. So what if you have n? So you got n minus 1 over n should be less than pi over n. That's right. Yeah. So for this to work, you want n to be less than pi plus 1. So this is slightly greater than 4. So what does it mean? That means, for example, if the speed ratio is like 4.1, this straight strategy still works. Student swims around the smallest circle, places himself on the opposite side from the teacher, and then swims along the diagonal. So that strategy works as long as this condition is satisfied. Okay? So let me just put the statement here, and then we'll revisit it later on. So one strategy works. Works if n is less than pi plus 1. But what happens if the n is larger than that? So if n is larger, that means this strategy doesn't work, but does that mean there is no other strategy? And the answer is yes, there is some other strategy, which is even smarter than this one. But in order to find that strategy, you need to be a little bit more familiar with functionals, and again, not so much variations, but at least understand the concept, how to minimize functionals. So this is something I'd like to postpone, since we're not, discussing this problem today in full. But I just wanted to bring everybody on the same page, so that you all can start thinking about question 2. Okay. I encourage you to write that functional down. Right, the amount you can compare the times. So for the distance. So assume that student. So just to be clear, fixed teacher speed, you can like set it to 1 or whatever for simplicity. Then student speed would be 1 over n. Okay, and then is it clear that there is no point for student to swim any slower than 1 over n? Like, it makes sense for student to always swim at his possible maximum possible speed. Is that clear? So, and that actually simplifies math a lot. So you assume that student always swims at that particular speed, and he only basically just chooses direction in which to swim. Okay, so pick some curve, whatever random curve. You can parameterize that curve, for example, in polar coordinates. There's radius in terms of angle. And for a given curve, assuming that the student always swims with the fastest possible speed, you can actually find the time for the student to get there. Does that make sense? And then, of course, you need to find for the teacher to get to the end point of that curve. Again, disclaimer, that end point is not going to be on this diameter. So you just need to pick like a curve, including the end point. And from that, you'll be able to write both times. Teacher's time is pretty straightforward. Student time, you'll need to write some kind of integral. Is that making sense so far? Okay, so when you write that integral, that will be the functional, and we can work with it. But I want everybody like to think about it and construct the functional. So that way your brain will be warmed up for the solution. Okay, is everything clear about what to do next? Okay, so basically the way I solve this problem, by the way, I think we had a competition with friends. So this was like the first iteration that we soon discovered that n has to be like the speed ratio needs to be at least pi plus 1. And then somebody would come up with some other strategy meaning the curve, basically. Okay, so somebody would come up with a curve and say, okay, I found n that's like, 4.3 or whatever. And then somebody else, oh, I found a curve that's 4.4 until I actually found the precise maximum value. So this is, I should say, just to simplify your life, it's less than 5. N is less than 5, but larger than this. So, okay, just to limit your range of possibilities. And like I said, it's a transcendental number. Okay, any questions about this? No? Okay. Oh, and just to be clear, so the curve starts from this circle. So once you fix n, that fixes the small circle. So you assume that student starts from there. Okay. Because that's still the best position to start from. So the variability starts from the circle. Okay, like the generalizations of this problem, they basically all, well, not all, but at least the fox and rabbit variations can be solved using the same idea, that x plus z is a constant. Basically, what changes with the new givens is x and z initial. So you plug in the new values of x initial and z initial, and find the finals. Okay, and I think almost everybody who attempted this problem did it correctly. But like I said, not everybody attempted it. So make sure you do. I'm just gonna put this extra hint in here. So maybe not on this page, I guess. Yeah, this page. So, right. New x initial and z initial, and find x final is equal z final, so as before. Those of you who did it, let me just give you a bonus question on top of this. So suppose that the moment the fox fox starts chasing the rabbit starts running at an angle to the original line. Okay. Rabbit turns, still runs straight. So he only turns once, okay? Turns by angle alpha. Okay? So given the alpha, find the final distance. Okay, now let's talk about the plane. Oh, maybe actually let's talk about the puck. I don't think anybody solved it, but you correct me if I'm mistaken. Has anybody solved the puck problem? Actually, you know what? Let me, folks, quickly survey you, because maybe it makes sense for us to push this problem back a little bit. I understand some of you have not taken physics yet, right? You told me last time. So we were talking about forces, but is somebody not comfortable with forces yet? This is what I was planning to discuss today anyway. Oh, so everybody is okay with Newton's laws and everything? Yeah, Leon, it's hard to tell from your face whether you're joking or not. Okay, then tell me, folks, what does it mean that mu equals tangent theta? What's so special about it? Yeah, you can say that it doesn't immediately ring a bell, then we'll talk about it. But well, the puck is kicked, so it will slide. Right, but what does that imply physically? Okay, we'll postpone this problem. Okay, because yeah, there is one neat fact about this, and if you just know it, things are so much easier to understand. Okay, so then let's talk about the plane. I don't think anybody solved the plane problem. So the idea is to use actually the same equations as before, but not assume that v equal u. So if you look at these equations, 1 and 2, they're still true. Just don't put v equal u. So yeah, let me put that. If it worked, don't. So sure what's happening. So just treat them as separate given things. And then you can still massage these two equations. No, not quite. Yeah, Leon, well, almost there. So, but yeah, well, let's discuss it all together. So let's focus on the plane problem for now. So this is what you can play with these equations, 1 and 2. So basically, I want to get rid of the trig part because the right-hand side is constant except for theta. And you see there is minus cos plus cos. The idea is to get rid of it. When u equals v, you simply add the equations, but then, folks, are you seeing what I'm heading to yet? So what do I need to do with the equations?
Wait, was my solution in my submission like close?
Alvin,
Where?
you?
Hmm?
Trying to see who's speaking. Is that Alvin?
Yeah.
Let me check.
So basically, I found t in terms of z and theta, and then I found z in terms of theta, and then I plugged it in and I tried to do theta equals 2, 0. But then that somehow went wrong.
I don't remember exactly what you did, but I don't think you finished. Let me check.
Like something went wrong in the middle.
Oh, and about the tan theta thing, I think the significance of that is that if you draw out the force body diagram, or the free body diagram, I mean, you'll get that the gravity splits up into g cosine theta perpendicular to the slope and g sine theta parallel to the slope. And then if you do m1g cosine theta times tan theta, the frictional force is m1g sine theta, and that cancels out with the gravitational force. So then it won't slide down. That what it means?
Okay, yes, this is it. This is the main thing. Like I said, we'll come back to this problem. I want to make sure everybody's on the same page, right? So Abhijit got it right, but I want to make sure it makes sense to everybody. Okay, I'm looking at your solution, Alvin. Yeah, okay, so you try to consider a limit, L'Hopital's rule, and somehow you got a 0, which doesn't seem realistic, right?
Yeah, so like I'm thinking there's some math error that I didn't catch somewhere in the middle, but
honestly, I'm not familiar with this approach. So of course it exists, like the brute force approach exists in this question as well. But well, let's try to use the neat trick, because this is the goal, folks. I want you to learn that trick. So, oh wait, is my annotation gone? Well, hopefully you wrote it down, haven't you? Okay, maybe we start from the opposite end. So for the plane, what do we expect? Let's just have some limiting case that we could check our answer against once we got it. For example, if u is much larger than v, how long do we expect it to take for the missile to hit the plane? If u is much greater than v, we expect the time to be what? Remember, h was the height.
T is about h over u.
Exactly. So obviously, in general, it also depends on v, but it should reduce to this answer when v is 0, or like negligible compared to, okay? So this is good to have. And folks, it's a general strategy. If you see a problem, again, that doesn't apply to f equals ma because it's just multiple choice. But the second round, even if you can't solve the problem and have no idea how to approach, but you know what to expect in some limiting cases, just put it down. It never hurts. It may get you some points. And those some points may be critical that distinguish you from like the other students and get you just a little bit above to make the cut. Okay. So anyhow, I asked that question and I thought that Alvin had the answer, but you had a few extra minutes to think. Do you see what we can do with these equations to get rid of the theta? Again, we don't know if it's going to be helpful, but this is a step that we want to take. Okay, so you look at this problem, you see some variables that you can get rid of. Let's do it and then see what we can do next. So folks, well, what combination will do that?
V times 1 plus u times 2.
Yeah. Equation 1 times v. Sorry. Sure. Equation 2 times u. What does it give us? So on the left-hand side, it gives us v dx dt plus u dz dt equals v squared minus u squared. You agree? Oops. Okay, now, like, how does this help? Well, let's rewrite this as ddt of whatever else is inside. That is vx plus uz equal v squared minus u squared. Now, this combo inside the parentheses is changing at a constant rate. Okay? That means delta of this, Vx plus Uz, can be written as V squared minus U squared times delta T, where delta is for the whole trip. And then from here, you can solve for delta T. So delta of Vx plus Uz over squared minus u squared. Now, this you can easily compute, right? The top you can compute, what is it? Folks, are you thinking or what? Just tell me, should I give you another minute?
Yeah, it's just UH over U squared minus V squared, right?
VH,
UH.
right? UH.
Yeah.
That's right.
Well, it's
The
actually
whole
negative.
thing?
It's actually negative.
Okay, that's better because you see the denominator is negative.
Yeah, but I switched around the terms in the denominator, so.
Uh-huh. Okay, folks, do you agree with this? Yeah, remember delta x is negative h over 2. Okay. And delta z is positive h over 2. And I'm getting what you're getting. What am I missing? Okay, I leave it to you to finish. Let's take a break, a 10-minute break. And after the break, we'll finish this off and start the new piece, okay? Okay, is everybody back? Yeah, I agree. First off, I agree with Elvin. I somehow was thinking about something else. So delta x is actually 0 and delta z is -4. I was somehow thinking about the fox and rabbit still, but for the Miss Island plane, x starts at 0 and at the end x is still 0. So delta x is 0 in that equation. Now delta z, it's originally so delta z is equal negative r. So, or sorry, negative h, and that's what the Alvin got. So yeah, that's the answer. So let me pull it up again. So the time to hit the plane is hu over u squared minus v squared. Okay. So you can check our expectation was that when v is negligible, delta t equals h over u, and you see that works, right? So if you neglect v squared on the bottom, you indeed get h over u for the time. At the same time, if you see, if you check what happens when u approaches v, the time blows up, which makes sense, right? When u is equal to v, it never happens, right? It takes an infinite amount of time to catch up with the plane. Okay, folks, you good here? Have any questions? No? Okay. So now let's start the new material. Again, I'll then just quickly summarize everything that we need to know about forces, and then we'll revisit that part problem. Okay, Newton's laws. Okay, again, I'm not sure how exactly you were presented these. The catch is that what Newton stated as his laws, we modified. So what I'll talk about is so-called the modern formulation of Newton's laws. And you tell me if that's the same as you were taught or not. So first off, there is law of inertia, which is not in Newton's law anymore. So I'm going to call it like law number 0. This used to be his first law in his own statement, but not anymore. So law of inertia. A point particle. Did I introduce this abbreviation, PP?
No.
If not, that I'm going to do it now. PP will stand for point particle. Okay, so point particle will move at constant velocity vector typically people add this phrase. I'm going to add that too, but in parentheses, or remain at rest if not acted upon by forces or all forces are balanced. Okay, so the last piece is clear, right? You know, in reality, you hardly ever have a situation when there are no forces, but a situation when you do have forces, but their balance is quite more common. Now, remain at rest, why did I put it in parentheses? Because clearly it's a partial case of constant velocity. So it's a redundancy really, right? Constant velocity, put that constant to 0 and you got remaining at rest. The modification that we made to Newton's first statement is that Newton talked about bodies. We talk about point particles. So let me just quickly illustrate why it may not be true. For bodies, first off, you understand spinning. If something is spinning, that means it's not going at constant velocity. There is acceleration. So if you throw a frisbee in outer space, far away from any planets or stars or anything, there will be no forces, right? So the second part of law of inertia is satisfied, but some points on the frisbee will not be moving in a straight line, constant velocity. So Newton's laws really should be stated for point particles. Okay, generalizations are not always working. Now, tell me, is law of inertia always true? Does it always hold?
Well, none of them hold in a non-inertial frame.
Exactly. So here is the catch, right? So we used to talk about inertial frames as frames that are moving with a constant velocity with respect to laboratory frame. But then you run into this issue, what do you define as a laboratory frame? Right? What's like the ultimate absolute frame with respect to which the inertial frame should be moving? And there is no good answer to that. I mean, there is a satisfactory answer to that, but that's after Newton. And I'll probably come back to this point a bit later. So for now, you're absolutely right. If you have a non-inertial frame, the law of inertia doesn't hold. Can you give me an example?
Like if you're in a car and the car is accelerating.
Okay, and how do you know it's not holding? Like, can you elaborate?
Wait, sorry, could you repeat the question?
Can you just elaborate why law of inertia doesn't hold in an accelerating car? Just give a specific example.
Okay, so in a non-inertial frame of reference, there might be no forces acting on it, but then it's not moving at a constant velocity anyways with respect to like the ground, because the frame of reference itself is accelerating.
Uh-huh.
And it's moving at constant v with respect to the frame.
Let's see, somebody put something in the chat. Let me check it out. Okay, that's another good example, Leon. Let's talk about that as well. So let me just put what Alvin said here. Yeah, so if you consider something like you know, have a ball, put it on the table, maybe not in the car, but on the train is accelerating. the ball will start rolling all of a sudden. So it will have acceleration with no force acting on it. Okay. Merry-go-round is another good example. Just talking about centripetal acceleration. So what happens on the merry-go-round? There are a couple of things. I think we briefly discussed them in the spring anyway, but it's still worth revisiting. It's probably next time. So what happens on the merry-go-round? So
you like slide towards the edge, or like you feel a force that pushes you towards the edge.
You feel a force that pushes you off to the edge, even though there is no physical force acting. So that's another example of force of inertia. In this particular case, this is centrifugal force. And once you and think of a bowling ball for simplicity. So once the bowling ball starts rolling off, there is yet an additional force of inertia. Who knows what that force is? And which
rolling off? Wait, what?
So if the ball starts going along the radius, doesn't really matter whether it's toward the center or away, let's say away, then there is one more force on top of the centrifugal force. Okay, some people are putting things in the chat. Yes. Yeah, you need to work on your spelling, Leon, but yes, that's right. Coriolis force. Coriolis is a German physicist. And that force
I've
is
heard of that before, but like, I don't know what it is.
Yeah. So we'll revisit it when we get to like systematically studying forces of inertia. Yes, thank you. So that force is, just think about it. If you roll the ball off and like put it in the paint so it leaves a trace on the merry-go-round, the trajectory will not be radial, right? It will be bending backwards. And you can interpret that as that extra force of inertia, specifically Coriolis force. So again, we'll come back to this. So here comes a nice constructive method to determine whether reference frame is inertial or not. So why do we need that? Let me spend like 5 minutes putting like important philosophy in place. As you know, like, so yeah, well, let's start with this. Let's start with the negative, and then we'll get constructive. So, is Earth inertial frame? Everything you do like in school physics labs, you assume that Earth is a good frame, right? You do your labs and you compute things, and they work pretty well. So it seems that Earth is working as an inertial frame, but yes, Leon, Earth spins. So it cannot be considered an inertial frame. Who was the first person who demonstrated that, like experimentally?
Was it Foucault?
Yeah, Foucault. So it's a French name, so half of the letters are not pronounced. Yes, Foucault pendulum was the setup that demonstrated that Earth was actually spinning, and you could not use it as an inertial frame. It's not actually how we say things in physics. It's not that you can't use it. The question is, it's a model. Assuming that Earth is an inertial frame is a model. The question is how accurate this model is. It's obviously accurate enough for your labs, okay? But it may not be accurate enough for some other things. So just think about it. There is no like black and white in physics. There is a gray area related to the desired accuracy. Okay, so Foucault pendulum was that device, and everybody knows what that is. The main feature of this pendulum, it needs to be pretty long. The very first Foucault pendulum, as you can tell from the name, was in Paris, in Notre Dame de Paris. In the US, pretty much every self-respecting science museum has it. Boston's Museum of Science has it. In Philadelphia, we have Franklin Institute. I'm actually not sure about New York. Do you guys know if you have it somewhere?
In New York, I don't know. In the US, there's a famous one in Smithsonian.
Of course, yeah. Like I said,
apparently Cornell has one, according to Leon.
Oh. Yeah. Yeah, there were multiple museums in the country or observatories which have them. So find out if there is one in New York. It would be kind of disappointing if you don't have one. And you know how it works, right? The original pendulum had a basket with sand and there was a little hole. So the pendulum was swinging and leaving a sand trace on the ground. And because the earth was spinning, that trace was not directly straight. It was bending, 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 bending. And after a while, it actually repeated the trace. So Earth is spinning. It's not a good inertial frame for some experiment. The sweeten the pill, Earth is spinning not very fast, right? It takes 24 hours to complete one revolution. So it's not a super significant acceleration. So for many practical purposes, it's good enough, but obviously not for everything. So if Earth is not good enough frame, people started looking at the sun, heliocentric system, and they realized, yes, sun is good enough for like Earth orbiting the sun or planetary motion, but of course, sun itself is moving around the center of the Milky Way galaxy. By the way, do you guys have a sense of scale, like how fast the Earth is moving when orbiting the sun?
Pretty fast.
It's like 30 kilometers per hour or something.
Say it again?
Or like, it's like 30 meters per second or something like that.
30 kilometers per second.
Yeah, 30 kilometers.
That sounds fast.
It is, yeah. So it's like 20 miles per second, if that helps. So I estimate it's about like 70 miles from you and me. So it would take 3.5 seconds for Earth, just sitting on Earth, to move that distance. But if you talk about the sun orbiting the center of the Milky Way galaxy, it's going even fast. That's 200 kilometers per second. And it's also spinning. So you would say, oh, sun is not an inertial frame either. And again, it's all a matter of accuracy. But of course, if your accuracy requirements are very, very high, then you want to consider something else. You may want to consider the center of the Milky Way galaxy as your reference frame. And then by the same logic, Milky Way galaxy moves itself. So you need to reconsider. So this is what Mach was talking about in his criticism of Newton. Do you know who Mach was? Does that ring a bell, this name? German philosopher and a little bit physicist. Yes. Yeah, it has to do with the speed of sound. So Mach did something about sound. So it's a unit of speed. So 1 Mach means speed equals speed of sound. 2 Mach means twice as fast, and so on. So it's a convenient unit, especially when talking about supersonic plane. But Mach was like a pretty famous philosopher, and he set a conceptual foundation for general theory of relativity. So you can think of like Mach to Einstein is like Galileo to Newton. But Mike criticized Newton a lot because if you know the story, Newton actually gave up. He didn't find a satisfactory answer. He kind of came with a lame example, or lame explanation. He had this experiment of bucket with water that was spinning around the vertical axis, and you can probably visualize what happens. What happens with water when you spin that bucket?
The centrifugal force pushes it to the outside.
Again, we don't officially know that yet, but you're right. So the water, do you know what the shape is actually?
Shape of the water?
Yep.
It's like the 3D parabola thing.
Yep, it's parabolic. Yes, thank you, Leon. So yeah, the shape becomes parabolic, and again, there is
Oh, the surface of the water. Okay.
the surface. Yes, the shape of the surface of the water. It's parabolic. So how would Newton explain it? So it's spinning with respect to what, right? What is the, like, and he would say, oh, there is absolute space. So this is spinning with respect to absolute space. That's why there are forces of inertia, centrifugal forces in this case, that push the water off the center. But as we know, such thing doesn't really exist. Absolute space doesn't really exist. And Mach was the first person to criticize that and propose conceptual approach, and that all crystallized with Einstein's general theory of relativity, where we know space and time are dynamical entities, all dependent on each other and on matter. So there is no such thing as absolute fixed space. But again, on the bright side, Mach came up with this constructive principle. He said, you first decide what experiment you need to do. And for that experiment, you can always find a good frame, good enough frame with the desired accuracy that you can call inertial or inertial enough, so to speak. Okay? And let me just put it in some simple words here. Can always find a good enough frame. And that crystallized and became Newton's first law in the modern formulation. Oh, and appreciate this definition. What do we call inertial frame now? Inertial frame is such a frame in which law of inertia holds. Very simple and straightforward. How do you check if law of inertia holds? There is another simple experiment. Have you guys seen the movie Inception? Nobody? With DiCaprio, nested, Alan, you have. So it was about sleeping and being in somebody else's sleep, and sleep inside sleep, and so on. So the main character had a method of finding out whether he was in his own sleep or somebody else's sleep. So what was that, Alan?
Was it the top that he had?
Yeah, he had a spinning top that was actually non-symmetric or imbalanced or something that was not supposed to spin. But he knew that, so in his sleep that wouldn't spin. But if he was in somebody else's sleep who did not know that this top is imbalanced, it would spin. So that was his mechanism to find out whether his reference frame was good or not. So we have a similar mechanism here. Just take a ball, put on the table, and if it doesn't accelerate for no apparent reason, the frame is good enough. It's inertial. If it starts accelerating for no apparent reason with no forces present, then the frame is not inertial. Okay, so it's a very constructive, practical approach. It's not abstract anymore. So you can clearly tell if frame is inertial. Okay, so What we now call Newton's first law is this. Basically says inertial reference frames exist. And IRF stands for inertial reference frame. I mean, if I elaborate, I should say there exist reference frames called inertial such that an object will move at a constant velocity or remain at rest if not acted upon by forces or forces are balanced. So this is the complete statement of Newton's first law in its modern formulation. It later translated to the first Einstein's law for general theory of relativity, where he generalized the statement not just for laws of mechanics, but for laws of all physics. Okay? Actually, even in special relativity. Okay, so Newton's first law really is just this. It's Mach's principle, unlike what you equivalence principle is something else. Well, I guess some version of it, yes, yeah. Anyhow, I'm not exactly sure how it was presented to you in school. A lot of people confuse law of inertia and Newton's first law. Yes, Newton confused them, but we don't. Now, has zero problem solving power, but it sets the foundation for Newton's second and third law so that we can actually solve problems. So this one is easy, right? So it seems. F net equals ma. However, Newton didn't write that. Newton wrote F net. Does anybody know what Newton actually wrote as his second law?
dp dt.
Thank you very much, exactly. And that becomes critical. Again, we don't know momentum yet, officially, but at least let me put that on the side. We'll come back to this. We know that P equals mv. So if m is constant, then of course dp dt is simply m dv dt, which is ma. Okay, so then it doesn't really matter how you write it, first way or the second way. But as you can imagine, mass does not have to be constant. Then you have an extra term. Remind me, did we discuss this in spring or not?
I think we did.
Okay, but not everybody here was with us in the spring.
Yeah.
Okay, so again, we'll revisit it. If m is not constant, you get extra term. And you have a question like, what is more accurate? So the answer is this. This is more accurate. Okay. And then Newton's third law. So F net is the total of all forces acting on a single object. Newton's third law is about two interacting objects. So if you have two interacting objects, they exert equal and opposite forces on one another. Again, that's what Newton said. He talked about objects and he just stopped here. However, we need to make that more accurate as well. So if you label the objects 1 and 2, this force will be labeled as force 2 on 1, and this is force 1 on 2. And just remember, whenever you say there is a real force, that means you should be able to present the two objects or an object and an agent or a field that interact with that force. If you can't present the second object, that means it's not a real force. Like forces of inertia, right? When the car is accelerating, you feel that you're being pushed back. but you cannot really identify an agent that's doing it to you. There is nothing that's pushing on your chest, right? That's how you know this force is not real. This force is a force of inertia associated with the reference frame, okay? So this should save you some trouble when identifying forces. Okay, so let's just make this precise. F12 equals negative F21, and they're directed along the lines connecting the particles. Directed along the line 1, 2. Why is this important? Can anybody explain what happens if you have sideway forces like this? They still equal and opposite, right?
A torque.
But there's something strange about this.
You have to balance torque.
Yeah, there will be an imbalanced torque. So if you were to put these two particles on a stick, right, that stick would be spinning forever. So it's like free energy for you, right? If you find a way to convert that to heat, for example, you can boil water for free. So this is not really happening in real life. That's why we added this phrase. And this phrase has actually to do with conservation of angular momentum. Okay, so when we transition to conservation laws, they're more fundamental than Newton's laws. So we'll talk about conservation of energy momentum and angular momentum. And then, of course, some of you already know that if you switch to Lagrangian mechanics, that's even more fundamental. Okay, so this is it. This is the summary of Newton's laws that allows to solve problems. And let me just get back to that incline example, just make sure everybody's on the same page there. Folks, do you have any questions about this? Okay. So force of friction. Again, just a quick reminder that force of friction is given by, it's proportional to the normal force because, again, they're like cousins. These are both contact forces between the surface and the object that's in contact with the surface. Normal force is perpendicular, friction is parallel, and they are proportional to one another. So typical way to write it is this. Friction equals mu times n is the normal force. And then, of course, we distinguish static friction and kinetic friction. But that's not super important for this problem, okay? So this is incline. Angle theta. Here is a block on the incline. I know most of you have gone through this, so I'll be real quick. There is a downward force, force of gravity, mg, and there is normal force, that is perpendicular. In fact, the word normal, as you know, is synonym of the word perpendicular. And there is friction up the hill. So here is the setup. This ramp, you can change the angle. Okay, you can lift the ramp until the block slides. So you capture the moment when it starts barely sliding. Okay. So this is the setup. Increase theta until the block slides, like barely slides. Okay. So given whatever you need, mg theta, actually, let's put it the other way around. So yeah, theta, we want to find the coefficient of friction. Again, you know the answer, but let me just illustrate how it comes up, just to make sure we're on the same page. And normally, whenever you solve problems on forces, you stick with the same strategy. I'll state it as a three-step strategy. And those of you who were here in the spring probably already know it. So step number one, identify all forces acting on a given object. And plot a free body diagram. Given object. And plot the free body diagram. In step two, you use Newton's second law and write F net equals ma, after which you expand F net in terms of all the forces you've identified in step one. Okay. And then this is a vector equation. You want to extract scalar equations. So if it's two-dimensional problem, this is actually two equations. And the way you extract it, you choose coordinate choose coordinates, x and y, for example, and project. And project equation star onto x and y prime. Okay, checks it. And after that, physics is over. You do the math. So let's see how this works here. We already finished step one, really. We have the forces. And then you folks probably know what is a good frame here. What is it?
X along the incline and Y perpendicular.
Very good. We're still sticking with the rectilinear frame, which means they're orthogonal to one another, but they don't have to be horizontal and parallel. And in order to avoid confusion, I'm gonna call them X prime and Y prime. Okay, so we don't confuse them with the regular X and Y. So what do we have here? We have friction plus normal force plus mg equal ma. This is our equation star. Now we need to project this equation onto x prime and y prime. So who wants to spell it out, the x prime projection of this equation?
So the block isn't moving. So then F, the frictional force, plus mg times sine of theta.
Okay, normal force, I'm going to put a 0, right? Just for the sake of bookkeeping. Now, mg, well, how does that project?
Mg sine theta.
Plus or minus?
Plus.
Okay. Then I'm a little bit puzzled because F and mg sine theta should be in opposite directions.
Yeah, but
One
then
of them
F is
had-
negative, right?
Okay, friction is negative, good. Now, what about acceleration?
0.
Okay. What about y prime? Maybe somebody else will spell it out. Abhijit, do you want to say something? You seem to be muted. Actually, you're not muted, but for some reason there is no sound. Is it just me, or you guys don't hear Abhijit either?
I don't hear him either.
Oh. Well, then somebody else please spell it out. Well, then, do you want to continue then?
Okay, so we have n minus mg cosine theta
Again, it is 0 plus, right? Minus mg cos theta. And what do I put here?
0 as well.
Okay, 0 as well. Okay, then we can, from here we gather that f equals mg sine theta. From here we get that n equals mg cos theta. And we know that mu is friction over normal force. So if you divide this by this, you have everything canceled,
Tan theta.
therefore tan theta. So this is that magic relationship between mu and tangent theta that you've seen before. So the angle is actually called critical angle. Okay, the angle at which it starts sliding is critical angle, and the critical angle is related to mu through this formula. Okay, so what does it mean for us in the context of that problem about the puck? Exactly as some of you explained, the component of gravity that is parallel to the incline, mg sine theta, equals to force of friction. Does that make sense? So that's all we need to know. So let me just put that remark in here. For the puck problem, F equals mg parallel. The component of g that's parallel to the incline, the one that's relevant for motion of the puck. Okay, I hope this is enough for you to finish that problem, but do tell me if things are still not clear.
Well, yeah, then in the puck problem, the initial velocity is sideways, and then the frictional force goes against motion, right? So it's not always just going to point upwards. It's going to point like upwards and to the side. So it's not going to be like completely. It's not going to stop because
You're right. It's not going to stop.
Component.
So let's just let's say this is gravity, right? And then this is and then this is friction, initial friction. So this is mg parallel, and this is friction. And they're equal. And then what happens? Yeah, the puck is kicked with some velocity v to the side. What happens next moment? Well, where does the puck go?
Keeps going to the right until the force of friction slows it down to 0.
Well, let's understand. So friction slows it down horizontally. What does gravity do?
It makes the velocity vectors smaller and point downwards more.
Okay.
Yes,
So
but that cancels out with the parallel friction.
So let's be careful. So the next moment the puck is moved, but let's trace the velocity. The velocity tilts down, right? It's slightly shorter on the x and has a little y component now. Okay? So this is V1. Now let's do the force diagram. Gravity is still pointing down, exactly the same thing as before. Where is friction pointing?
Opposite
Along.
V1.
Yeah, it's also tilted, right? It's now at an angle. So importantly, magnitude-wise, these guys stay equal, right? Friction stays equal, and so on. Okay, what happens next with velocity and the forces?
So it's going to keep rotating, right?
Yes, it's going to keep rotating. Now, if you wait for a long time, what's going to happen?
It's going to stop because friction is going to drain out all the velocity.
Okay, let's not talk about velocity. Eventually, so friction kills the x velocity, right?
Yeah.
And it's the only force in the x direction. So eventually, the x velocity will be killed, right? That means it will be pointing straight down the incline. I'm not sure how long it will be. That's exactly the question. Okay. But the final is straight down. For the forces, that means, again, gravity is still same as before. Where is friction pointing?
Upwards?
Straight up. And what is the net force now?
0.
0. Okay. That means what? What will be happening to the puck?
It's going to be just going constant velocity straight down the...
Exactly. F net is 0 at this point. That means V final is just constant. We can call it terminal velocity, even as a vector. And since velocity keeps pointing down, friction keeps pointing up, so this is still true. So things just stay stable. Okay? But it's natural to assume that V final is slower than V naught. The question is, what is it? Find V final, the magnitude of V final. Okay, folks, do you feel you know how to continue? Okay, take it as a no. Okay, one more hand. Just use the same type of axis as the fox and rabbit problem. Okay, one axis could be straight down and fixed, and the other would be aligned with the friction. And instead of writing delta in positions or distances as you did for the rabbit, you would be writing what?
It'd be like d plus dz.
You would be writing delta v's. Okay, and remember two delta v's, one for the vertical axis, you can call it y, and then you can call the other axis z. So you'll be writing delta vz and delta vy. Just write it down carefully in terms of forces, or you can write time derivatives for vy and vz. And once you wrote those equations, the rest should be clear, okay? Just write those equations down and
So is this without friction? Maybe that's why I was confused. Is this without friction or with friction?
no, if there was no friction, it wouldn't be interesting. Without friction,
Well, so what is mu?
Mu is the coefficient of friction.
No.
I mean,
Like, what is
you don't
it?
need to use it. You don't need to use it. You only need to know that it's equal to tangent theta.
Mm-hmm.
That sets these two forces equal.
So then why does it still go down? How does the velocity change downwards if they balance out?
Yeah, they balance out. That means velocity stays constant.
Mm-hmm. But then why does it change direction?
Well, originally, okay, let's go back to the first picture. In the first picture, v is to the right, f is to the left. That means f, being the only force in the x direction, it slows v down.
Mm-hmm.
Gravity, on the other hand, accelerates it a little bit. So it provides a vertical negative component to velocity. So the next moment, velocity looks like this. It's slightly tilted down. And it may have changed its length. We don't know yet, okay? The answer is yes, it will be slower. But importantly, the direction is changed, okay? And it keeps happening until the velocity becomes straight down. At that point, friction turns straight up, starts canceling gravity, and after that, nothing changes. Right? The net force is zero, velocity stays constant. That means force of friction stays constant in direction. And, you know, it's a cycle. Everything stays constant after that. Does that make sense?
After that, it just keeps sliding down at that.
Yep.
Okay.
Yep. So the question is find that final terminal speed at which it will be sliding down. Given the initial speed, you're given the v naught. So as a fraction of v naught. Some of you may already guess the answer, but of course I still want you to elaborate how you got it. Any guesses as to what the answer is?
V naught over 2.
Yep, that's right. That's right, but again, just do it the proper way. Elaborate, write the equation, and see how that comes up. Okay? Any other questions? Anybody? Okay, then. If not, then let's call it a day. So the hard